Hi, this is lecture 1 in chapter 28, slope deflection method. We're getting close to the end of the full course. It is 30 chapters and this is chapter 28. It's another long chapter and today is lecture number 1. So I'm going to have a little bit of introduction, give out the table of contents and I'm not sure if we can solve the examples today, but we'll see what we can do today. The table of contents, introduction to the slope deflection method, the sign convention, definition of fixed end moments, slope moment, sway moment. These are new terms. Steps of solution, and then examples for beams, examples for frames, structures with sway. Sway means like side displacement. Steps of solution and examples. Introduction. The slope deflection method is one of the methods used to solve statically indeterminate structures. And this method depends on finding the final moments, at the beginning and end of each member, and from which we draw the minimum moment diagram, the shear force diagram, and the minimum moment diagram. We'll just share the screen quickly to show you this one. We have this example. We have this, the screen is loading up. We have this example. We have this beam that has fixity, and a roller support, 6 and 1, 7 reactions, and the three equations of this force, or 4 times the statically indeterminate degree, or statically indeterminate structure to the fourth degree. So we want to draw the bending moment diagram for this beam, calculate the final bending moment diagrams using this slope deflection method at the beginning and end of each member. So we want to calculate MAB and MBA, MBC and MCB. So MAB, MBA, MBC, MCB. So they might be like this or like this, or like this. This one will be like this or like this. Another example for this one, we have fixity roller, 5 unknowns, twice statically indeterminate. So we want to draw the bending moment diagram for this beam, starting with the final moments, calculate the final moments using the slope deflection at the beginning and end of each member. So we want to calculate MAB, MBA, MBC, and we know that MCB equals 0 because we have a ruler over here and we don't have fixed moment. Even if we have fixed moment, M equal M of the fixed moment. Example for this frame, we will draw the bending moment diagram for the frame. We will calculate the final moments, MAB, MBA, MBC, MCB for this frame. Then draw the minimum moment diagram, then draw the shear force diagram and normal force diagram. How do you calculate the final moments? How do you calculate the final moments? The final moments is the summation of 3 parts. One is called fixed in the moment. The second one is called the slope moment, and the third one is called the sway moment. So to calculate the final moments, we know that we have to know that final moments equal 3 components: fixed end moment, slope moment, and sway moment. So we're going to explain each one. What's fixed end moment, what is slope moment, and what is sway moment. Fixed end moment, it is a moment coming out from the effect of loads or members. Okay. So this moment, the fixed end moment is, could either be calculated using consistent deformation method, or we could memorize the values related. The fixed end moments have been tabulated for many cases. So I mean, if the case we have matches one of the cases tabulated, so we can just take it out from the table. So we can either calculate it using consistent deformation method, for example, or go to the tables and get the fixed end moments from the table for the conditions of the beam and loading type and the span and so on. So these fixed end moments differ according to the shape of the member, to the load, to the length, to the support conditions, and we just go to the table and take these ones. Okay. So in exam setting, you could either be given the tables or you should memorize part of the or some of them. Okay, but most likely you will be given the tables, and then from the tables get the fixed in the moment for this case, and then move to the next step. The second moment, which is the slope moment, it is a moment that comes out due to the slope of the beam at the ends of the member. Okay, and there are also fixed laws or fixed rules to calculate the slope moment. And the slope, we will refer to the slope by theta because the slope is basically an angle. Okay, the sway moment, which is the third type of slope, which is part of the final moments. The sway moment is the moment that comes out due to sway of the member at the end of the member, which is horizontal displacement at the end of the member. This creates moments in the members. So the moment due to sway at the ends of the member creates the sway moment. And there are also some fixed laws or fixed rules to calculate the sway moment. And the sway moment will refer to it by delta capital, which is a small triangle. And the sway is a movement perpendicular to the member itself. So if the member is vertical column, the sway is horizontal. Okay. So again, back to the final moments. So the final moments or final moment equals fixed in the moments you could get from the tables. Slope moments you could get also from the tables and using some rules. And the sway moment you use it also you calculate it using final rules. Add them up together, get the final moments. What is the sign convention or sign rule? The sign convention is very easy. The sign convention for moments, if the rotation is with the goes along with the clockwise direction, or if the rotation in the clockwise direction, we have positive moments. If the rotation is in clockwise direction, we have positive moments. If the rotation is anti-clockwise, then we have negative moments. So positive moment for clockwise direction, negative moment for anti-clockwise direction or counter-clockwise direction. Okay, now we'll talk about fixed end moments. So we'll just share the screen again to show you this fixed end moment. Just a second. We'll share the screen to show you the fixed end moment. We'll share the screen to show you the fixed end moments. So we have these diagrams, different diagrams to calculate fixed end moments. So we have fixed members, either column or a beam, either column or a beam. The loading could be to the right or to the left. For beam, the load is usually down. So we have length L of the member and the load is W centimeter run and fixed in this is fixed beam or column. So there are two fixes at the ends of the member. So what is the fixed in the moment? It's WL square over 12. So it's this one is clockwise, this is one positive, this one is anti-clockwise, the lower one is anti-clockwise. So this is negative. Over here, positive, negative. Over here, uh, uh, this one is positive and this one is negative. So the fixed end moment, the fixed end moments are WL over square, 12, WL square over 12, WL square over 12. So this is the fixed end moment for fixed beam. Okay, what and UDL, uniformly distributed load on a fixed member. The fixed end moment is WL square over 12 on both ends. What about concentrated load on a fixed beam? For concentrated load on fixed beam or fixed column, either P is here or there, or P is down to the beam. The fixed in the moment is PL over 8, PL over 8, PL over 8. So if the load is like this, the fixed in moments are with the tail of the load. If the load is like this, they are with the tail of the load. If the load is like this, they are with the tail of the load. Same thing over here. The load is like this, so the moments are with the tail of the load. Load like this, the moments are with the tail of the load. Load is like this, the moments are with the tail of the load. Tail of the moment is the tail of the load. Okay, so either WL is square over 8 for fixed and uniform distributed load, or PL over 8 for fixed, and P concentrated load in the middle of the column or beam. What about P for fixed, but P is shifted, not in the middle. P is at the distance A from one of the supports and the distance B from the other support, and the length is L. The fixed end moments is P, A, B. So it is to the one when the load A is smaller than B. So it is no, it is P multiplied by the A, which is the distance close to the fixity, multiplied by B squared, which is the other distance, divided by L squared. So P A B squared over L squared. So this one is P B A squared over L squared. So P multiplied by A by B squared over L squared. P multiplied by B by A squared over L squared. So P multiplied by A by B squared over L squared. P multiplied by B multiplied by B by A squared, which is the far one divided by L squared. So it's better to memorize these ones than you have in handy when you start solving the equations. Okay, what about fixity, fixed supports, and we have two loads. Each one is in the middle third. So this one is one third from the left. This one is at one third from the right, or two thirds from the left. So we have two P's. They are dividing the beam into three different equal distances. L over 3, L over 3, L over 3. Total length is L. What is the fixed end moment for either a beam or a column? It is the 2PL over 9, 2PL over 9, 2PL over 9. Again, the tail of the moment is with the tail of the concentrated load. The tail here is above, so the tail to the moment is above, tail to the moment is above. Tail is on the left side of the beam, so tail of the moment is on the left side of the beam. The tail is on the right side of the beam, so the tail of the load and tail of the moment is on the right side of the beam. The value is 2PL over 8 for both sides. Okay, what about if we have fixed concentrated moment or fixed moment somewhere in the beam? So we have moment M. The tail of the moment is above or is on one side of the beam. The moment is at A and B, and the length is L. So the moment, the fixed end moment is actually one with and one against. So one with the moment direction, tail with the tail, and the other one is against the tail in the other direction. Okay, so they add up like this. So they add up like this. So this is this one, and this is this one. So they all rotate in the same direction. So this one and this one rotate in the same direction. Okay, so they all rotate in the same direction. Same direction. So M at A and B, A from the right, B from the left, A from the top, B from the down. And the moment fixed in moment closer to A is MB, 3A minus L over L squared. Over here is MA, here M multiplied by the far one, B by 3A, 3 the close one minus L over L. Here MA, the far one, 3B, the close one minus L over L. Same thing over L squared, I'm sorry, over L squared. Okay, because this should be dimensionless. This is square L, or dimension cancel out, and then we'll end up remaining with the same moment units. So moment over here is MB, the far one, 3A minus L over L squared, MA, the far one, 3B, which is the first one, minus L over L squared. So MA, and they all rotate in the same direction. So this one, the outer ones and the inner ones rotate in the same direction. The right one is in the same direction. The right one has the tail below. The left one has the tail above. So the right one has the tail below. Same like the applied moment. The left one has the tail above. The right one has the tail below. Same like the applied moment. And the left one has the tail above, and this one has the tail below. And these are the values. The right one is MB, which is the far distance. 3A, the close distance, minus L over L squared. The other one is MA multiplied by the far distance. 3b minus L divided by L squared. Okay, just be careful, memorize the direction of rotation of the concentrated moment M. M here is rotating clockwise. M here is rotating clockwise, but M over here is rotating anti-clockwise. M over here is rotating anti-clockwise, but M this one and M this one is rotating clockwise. Okay, so the one close to M has the same rotation, has the same rotation or tail above, tail in the same direction. The far one has tail in opposite direction. Okay, what about this one? We have inclined beam, fixed, and inclined beam. We have P but inclined beam, not horizontal beam, or inclined column, not horizontal column. P L over 2, L over 2. Moment is P L over 8, P L over 8. Same thing like the horizontal column. Same thing like this one, PL over 8. If we have a horizontal column with P in the middle, the fixed end moment is PL over 8, PL over 8. Tail is the same tail as the load. Tail is the same tail as the load. Tail is the same tail as the load. PL over 8, PL over 8. Same thing if the member is horizontal or vertical, or the member is horizontally inclined or vertically inclined. If the beam is inclined or the column is inclined, we have the same values, PL over 8, PL over 8 both sides, and the tail of the moment is the same as the tail of the load. Okay, so P L over 8, PL over 8 for the beam, PL over 8, PL over 8 for this column, P load is this direction, moment is this direction, so that the tail of the moment is the tail of the load, PL over 8, PL over 8. What about the inclined member? And we have W ton per meter run, vertical, but distributed over L dash. So we have L and L dash, which are parts of the equation. So WL is distributed over L dash, but perpendicular to L, vertical perpendicular to L. Over here, horizontal perpendicular to L, which is the vertical, and the incline is L dash. So a moment is, again, the tail of the load is the same tail of the moment. WL L dash over 12, same value for all of them. WL L dash over 12, like this. If the load is like this, then the moment is like this. If the load is like this, then the moment is like this, and then the moment is like this. Okay. What about the fixity, and triangular load? So we have fixity, triangular load. W on the left, 0 on the right. So we have an L over 2, L over 2. We have, I mean, this L over 2, we could just write down L. But anyways, double L squared over 20 and double L squared over 30. So the one close to the load is a bigger one, double L squared over 20. The one far from the load intensity is double L squared over 50. So this one close to the higher intensity of the load shares bigger or gets bigger portion, gets bigger moment, and the one far from it gets smaller moments. Over here, the load is like this with the intensity W over here on the right. So the here is W squared over 20, the bigger portion, away from the distribution or at the zero distribution, W squared over 30. Here we have W down below. So moment close to W is W squared over 20, the bigger value. Moment away from W is WL squared over 30, the smaller value. Fixed end moments continued. We're just reviewing this fixed, and then we have W and L. We have WL squared, W squared on each side. P load on horizontal beam fixed. We have PL over 8, PL over 8 on both sides. Two P's at 1/3 of the beam. We have 2PL over 9, 2PL over 9, the fixed end moment. P at A and B from the L. The one close to A is PA, B squared over L squared. The one close to B is PB, A squared over L squared. Fixed moment, fixed moment M. We have A on the right, B on the left, L is the length. The one close to A is MB, 3A minus L over L squared. The one close to B is MA, 3B minus L over L squared. Okay. What about displacement of the support? We haven't talked about this one yet. So the previous ones are review, but this is new. For fixed and displacement of the support, delta capital at one end and the length is L. So the moment close to it, they both rotate in the same direction. In this case, if it settles down from the right, then they rotate anti-clockwise. If they settle down from the left, then they rotate clockwise. So here they settle down from the right. Both rotate anti-clockwise. So delta at the deflection or settlement of the support, they call it settlement of the support. It's 6 EI over L squared multiplied by delta capital and 6 EI over L squared multiplied by the delta capital. Same value, but one the tail down, one the tail is above, or the same rotation, but one has the tail down, one has the tail above. This is for settlement of one of the supports. Okay, what about this triangular loading? Again, this is revision and we're adding some more loading. W on the left and 0 on the right, triangular loading. We have WL squared over 30, the one close to the W intensity. And the one at 0 W intensity, the moment at this is W squared over 30, which is a smaller moment than the one at the load. What about partially distributed load? W only covering L over 2 and the span is L. The moment at the W is 11 WL squared over 192. The moment away from the W is 5 WL squared over 192. So it's like more than twice as much. The one close to the load is higher than the one or more than twice the one away from the load. It's 11 WL squared over 192, 5 WL squared over 192. What about this fixed beam and inclined beam and W? W on vertical down or perpendicular to L, and L dash is the inclined portion. The moment on each side is the same. WL, which is the horizontal portion, but which is the one perpendicular to the load direction, multiplied by L dash the inclined length over 12. So WL L dash over 12 on both sides. Concentrated load on inclined beam. Same thing like concentrated load in the middle for horizontal beam. We have PL over 8, PL over 8, the fixed moments. So these are the values for fixed members. What about fixed hinged members? What about if we have fixed and hinged members? We conclude or deduce or get the values of fixed end moments for fixed hinges. So fixed hinge means that there is fixed end at the fixity and 0. I mean there is value at the hinge support. So for fixed hinge member it should be 0 actually, but this is just one step of the solution. So how to calculate fixed hinged members? How to get the fixed in the moments for fixed hinged members? Okay, we deduce or we get these ones by calculations. We then memorize them. So we solve with the member as if it is fixed. So fixed is W and L. We have WL square over 12, WL square over 6. At the hinge, we add the moment which is WL square over 12 in opposite direction. So WL square over 12 from the fixity and WL square over 12 the hinge minus WL square over 12. Okay. Then half of this moment goes to the other direction in the same rotation. Half of this moment goes to the other direction in the same rotation, in the same direction of rotation. And we call this one carryover moment. So we put this WL squared over 12, which is the one opposite direction at the hinge to correct this one and put half of it on the fixed side. So this is in the same direction of rotation. Okay, so here we add WL squared over 12. We carry over to the fixed half WL squared over 12. Then we add them up together by superposition. So moment over here at the hinge is 0, and over here is 1.5 WL squared over 12. Or 3 over 2, 24, which is WL squared over 8 actually. So 1.5 WL squared over 12, which is WL squared over 8. So how did you do this again? For fixed hinged members, we solve them as if they are fixed. WL square over 12, WL square over 12. And then we correct our mistake at the right. We add a moment which is in opposite direction at the hinge. So the summation at the hinge is zero. So we add this dotted red moment, double L square over 12